Well, thank you all of you for coming to the course. In this course, we are going to cover in the next 5 days the basics of reproducing kernel Hilbert spaces and some selected topics of their usage for machine learning. So in the next 5 days, we are only going to cover the basics and a few topics because there are many techniques that people have done in the last 30 years. We could very easily have a 1-year course just talking about these things. So in the next 5 days, we are going to discuss a few things. I'm going to go slowly and everything should be simple. But if you have any question or comment, please interrupt me and ask me. It's good that you follow everything. And yeah, so those are the main things. So yeah, okay, so maybe we can just get started. Reproducing kernel Hilbert spaces were formalized by Aaron Sayan. Let me see if I write it correctly. Sayan in the 50s. And then it was introduced in the field of machine learning by multiple people like 30 years ago, but maybe I can cite Babnik and collaborators in the 90s. Okay, so I like to mention this because some people might think that the machine learning is a very recent field, but it's not so much. So machine learning is something that has been developed for many years now. And for instance, the work of Babnik 30 years ago is still very relevant. And it's going to be some of the things we are going to discuss in the course. And for instance, I highly recommend you to read the book of Babnik. I think it's in the 95. At least the first chapters are very interesting. Okay, so this is like a little bit of history. And then the course we are going to start the course with some motivation why people would like to use reproducing kernel Hilbert spaces for machine learning. Then we will define these Hilbert spaces in a very simple scenario. So everything is just linear algebra, and you will see everything is very simple. Then we do it for the general case. I guess that will be tomorrow. And after that, we will come back to machine learning and talk about several applications. Okay, so let's start with the motivation. So the motivation is going to be supervised learning. So supervised learning, I guess most of you might be familiar with it, but just to recall, in supervised learning, we have two sets. We have a set X, and the elements of X are known as in multiple ways, like instances, attributes, variables. If you want to have an example in mind, you can think that this set is a subset of some Euclidean space. In most of the things we are going to do in this course, it does not need to be the case, but if you just want to have a mental picture of what these guys are, is a subset of RD. And then there is another set, Y, and this set, the elements of this set are called labels or classes. If we are talking about the classification. In this course, I will be discussing mostly classification. Most of the things can be used also integration. Indeed, some things are possibly more natural in the regression case, but just because I like classification better, we will be discussing about classification. So what happened in classification is that the set Y is finite. Indeed, for this course, this set is so we will be using the example of a binary classification, so that this set is just going to have two elements, and we are going to encode them as -1 and +1, because this is going to make the notation easier. Okay, so in a classification, just a finite set, for now, just two elements, and if this would be regression instead of classification, the difference is that Y would be all the real numbers, for instance. Okay, so if you want to have an example in mind of what kind of problems we will be interested in doing, you might think that you want to develop an algorithm that is able to determine if an email is spam or not. So you might want to have a spam filtering algorithm. So for that example, the set X would be emails, and then the set Y would correspond to the case in which the email is spam or not spam. Okay, just if you want to have a mental picture of what kind of problems we will be doing. Okay, so we have these two sets, and then what we want to do, we want to find a rule, a classification rule, that in this course is just going to be a function from X to Y. So we want to find a classification rule for that situation. In the case of the email filtering, is just a correspondence. So basically for each email, it will tell you if the email is spam or not spam. Everything very simple, but if you have questions about notation or anything, just let me know. Okay, so we want to find a classification rule that's a function like this. So without loss of generality, we can represent these functions as taking the sign of some other function f. Okay, and f, where should I put it? Let's put it here. F is just going to be a function from X to the real number. Okay, so any function like this is given by an expression like that. I think that's fairly obvious. So basically in this course, so that finding a classification rule H is the same as finding a function f that we are going to use this way. Okay, so in this course we will be talking a lot about functions from X to R. Okay, so these Hilbert spaces are going to be sets of functions from X to R. And one way to use them is to have a classification rule this way. Okay. So we will be interested in this kind of objects, and all the discussions are going to be about this type of objects. So if we are interested in doing classification rule will be like this. If we are interested in doing regression, this function is going to be already the rule. Right? So if we are doing regression, Y is already the real numbers. So the rule is already a function from X to R. So this is what we want to do. So we want to find a function like this, and we have what we have to find it. We have training samples. Okay. So we have some samples. People usually call them training samples. They are just pairs of x's and y's. Okay. So in order to find that rule, somebody give us all these samples. People call it training samples. These samples are just examples of pairs of x and y. So you can imagine if we are doing in this email filtering case, somebody gave us 1,000 emails and they tell us if they are spam or not. So we have both the x and the y. Okay, and that's also why it's called supervised learning, because somebody give us supervised examples in the sense that we know the x and we also know the true label or the true class. Okay. So we have a bunch of examples and then we want to find the rule, which is the same as finding this. Right. Okay, so how to do this? Let's see how to do this. Or just the main ideas of how people do it. So the most common approach to find that rule is known as empirical risk minimization. So in empirical risk minimization, the way you find the rule is by minimizing the average loss of the training examples that you have. Okay, so basically, we are going to find the rule, or the usual way to find the rule is by solving an optimization problem in which we try to find classification rules in this case, but since finding a classification rule is the same as finding this function f, we are trying to find a function f such that the average loss over the training samples of that f is as small as possible. Okay. Okay, so we have our n training samples, and then we try to find the f that minimizes the sum of the losses. This loss function can be many different things. If you want to have a natural example in mind, in classification, the natural loss is the 0-1 loss. So let's define it for general x and y. So the 0-1 loss is basically just counting if you are making a mistake or not. Right? So basically this loss is 0 if your rule is right, and is 1 if your rule is wrong. With the notation that we have introduced, basically this loss is going to be 0 if f of x has the same sign as y, right? And a compact way to write that is to say if y times f of x is a positive number, right? So that's why it's nice to have this encoding, because we can write things in a very compact way. So basically, if the sign of f of x is the same as y, our classification rule will be right, and that happens if the product of the two things is 40. Okay, and then the loss is going to be 1 if the signs are different. Okay. And it doesn't really matter where we put the case equals 0, but let's put it in this case. Right? So this is the 0-1 loss, and okay. And basically the plan here is to find a function that minimizes that average number of losses. Okay, so everything simple. So, okay, but as I guess most of you are imagining, if you try to do this sort of thing, this is problematic, right? So one of the problems with this type of trying to do something like this is like, well, I mean, if the functions I'm considering can be whatever, and also maybe this loss is like this, how I do this optimization may be very hard. So problems here. So how we go about and do this is a problem. Other type of problem is something that people call overfitting. Overfitting. The name overfitting might be a little bit misleading because the problem is not really that you are fitting too much. The problem is that what you do in training is not representative of what happens later during prediction. But we will be talking more about these things tomorrow or in a couple of days, but just to give an idea, what can go wrong here? So if I'm doing this optimization and f is just any function, right? If f is just any function from x to r, indeed solving this is very easy, right? So I can define a function, from x to r, and this function can be like for the xi's of my training set. What I can do is to make them go to the y, right? So these are +1 or -1, so this is okay. And then for the other x's, for the x's that are not in the training samples, I can do whatever I want. For instance, I can make all of them going to 1, right? So this is a perfectly valid function from x to r, right? This is a perfectly valid function, and this function solves this problem, right? Because if now I compute the loss of this function in the training examples, I'm always going to get 0, right? Because this is doing exactly what it should do. So basically, if now I evaluate this, I will have yi times yi. So the yi squared is always going to be positive. So this rule is doing perfectly well in the training examples, right? So this quantity here will be 0 for this function, and 0 is the smallest value that this thing can take. So this f star is a solution of this. But as you can imagine, this if we use this as our classification rule, this will work very poorly, right? Because in these examples, it will be perfect, but I mean, these examples, we already know what is the true ISO. I mean, it depends on the problem, right? But in most of the cases, if we try to use this rule in other examples, it will always tell me that the email is not a spam, and then this is not really reasonable email filtering algorithm, right? So this function solves this, but this is very bad. This kind of problems is what people call overfitting. The problem is not really that this function is perfect in the training examples. The problem is that what this function does in the different examples is not related to what it does in the training example. So this function is not as smooth. Okay, so we will be talking about functions that are smooth. So basically, the functions that we are going to consider are going to be smooth for some notion of smoothness. Okay, so these are the setting. Now let's keep going towards the single spaces, little by little. So basically, in here, the conclusion is that considering any function is not a good idea, right? So we are going to consider a constrained set of functions. So we will start with the most simple type of functions, and then we will generalize that. So as you can imagine, if I say the most simple functions, I guess most of you are guessing that we are going to start with a linear function. Okay, so let's just start with linear rules. So for this case, we actually need that x is in Rd. In the rest of the course, x will be whatever. Okay, so we are going to use functions that are linear. Okay, so that's why we need to have a linear structure for x. So the functions we are going to consider in this first example are going to be linear functions. And to be a linear function means that there is a vector mu. Where should I write it? Like this. So there is a vector mu such that the function is defined this way. Right? That's what makes a function to be linear. Right? So function is linear if it's like this for some vector in Rd. Right? The axis will be in Rd in this example. Right? So we are going to consider functions that are linear, so that the classification rule is just going to take the sign of that quantity. Okay, so this is a reasonable type of example, and then if we do this, the empirical risk minimization, we'll try to solve an optimization problem as I did before. And now, basically, the function or the classification rule is determined by this vector mu. So then we will be minimizing this sort of thing, and then we will be doing the optimization over possible vectors. Right. Indeed, okay, let's write the expression of this. In this case, it's just the same thing as before, substituting f by this quantity. So the loss is 0 if xi transpose mu is positive, and the loss will be 0 if that quantity is negative. Then just using the definition, the same thing as before. Okay. So, and this quantity here is somehow important. People call this margin. We are not going to discuss about these things, but this is the real number that we want to make it positive. I'm talking about the 0-1 loss in these examples, not because it's the most common type of loss used in practice, but just because it's one that is more natural to understand, right? Okay, so now we will be solving this, and in terms of the optimization problem, this is something more charitable, because now we will be solving an optimization problem in which we have the variables, the unknowns, and that seems easier thing to do than solving an optimization in which the unknown is a function. So, optimization problems where the unknown is a function is very complicated thing to do. Okay, so this is what we would do. And as you can imagine, in terms of overfitting, if we only consider this type of functions, we are not really going to have overfitting, because this type of functions with this type of functions, we cannot do the type of example I showed before, right? So if the functions we consider are very simple, or something like this, I cannot make the function to be right in all the training examples and then be whatever in the rest of the examples, right? What happens with this type of rules? Let's make a picture. So let's imagine that x is just a 2, right? So our points are points in the plane. Our x's are points in the plane. So let's imagine the x's are just points here. So the x's are points there, and then some of them are of class positive. Should I do this? Some of them are positive, some of them are negative. Positive level. Okay, so some are of class. So these are our training examples. Some of them are positive class, some of them are negative class. If we are considering only this type of rules, we are doing something very simple. So the functions we are considering are 0 in a hyperplane, right? That goes through the origin. And then basically, if mu is pointing in that direction, our classification rule will classify all the points above this line as positive and all the points below this line as negative. Right? Very simple. You can imagine with this type of rules, we cannot fit perfectly all the training examples, and then for the other cases do positive always, right? I mean, this is very simple type of rules. Of course, this is not an explanation of why we avoid overfitting. Tomorrow or the day after, we will discuss more precisely why we avoid overfitting. Okay, but that's the idea of this rule. So this is very simple. I guess as you are guessing, this is very simple, but maybe not so useful in practice, because in practice, the samples, the relation between the x and the y can be very complicated, and trying to use just something linear is not going to be enough, right? So let's see how to make these things work better in practice. How to make these classification rules to be more expressive. So this we are going to do using something. Let's call it a feature representation. Or mapping. If it's not easy to see what I write in the board, let me know and I will try to make it there. Okay, so in order to make these ideas to work better in practice, we are going to make it more complicated, but still keeping the nice properties of the linear case. So basically, what we are going to do is instead of using the original x, the original instance or covariates, etc., we are going to change the representation. So we are going to have a function from x to rd. But that we are going to change the x's by some other vector. Okay. And this will allow us also to use general sets x. Okay, because basically we are going to use the outputs here. So even if the instances are, I don't know, if x's are actual emails, not vectors, right? So if x is a actual email, or maybe x is a graph, or any object that you might think of, as long as you have a reasonably good representation, you can do classification or regression. Okay, so basically we represent the x's in some Euclidean space. And now let's see why is that a good idea, or what kind of representations are interesting. So the easiest example we can think of is an example in which this C is just So let's imagine that we are in the previous situation, and then we are just going to increase the dimensionality 1, and basically we are going to take the vector before into the vector in which we add 1. So this is the most simple example, right? So it seems that we have not achieved anything by doing this. This is too straightforward, right? But now what happens is that so the functions that we are going to consider, right? So after we do this change of representation, the linear functions now are going to be linear in the output of this feature mapping. So they are going to be linear in the feature space. And so this space here is known as a feature space. So they are going to be linear in feature space. And then if we are using just this very simple feature representation, what we achieve now is that right. So if we plot in this figure this type of, I don't know why I changed the order. So if we plot now this equation here, is something similar to what we had before, but now since we add a constant here, these equations are going to be hyperplanes, but hyperplanes that might not go through the origin, right? Basically, right? I guess this is okay. Let's do this. So basically, this f of x is going to be x1 mu1 plus x2 mu2 plus mu3, right? Just because we put a 1 before, after, right? So we increase the dimension 1, but now our classification rules are more expressive. At least now they don't need to go through the origin. This is not a huge advantage, but I mean, what we did was extremely simple. Okay, so as I said, this is the most simple example. Let's make an example that is still simple, but maybe more interesting. I guess you might already guess where we are going with these ideas. But let's make another example, just to verify things. So let's imagine that we are in a situation in which the examples of the positive class are near the origin, and then the examples of the negative class are farther from the origin, right? So if we are in a, if these are our training samples, if we try to use linear rules, there is not much we can do here, right? So if we cut this with a linear rule, it doesn't really matter which one we use here. Is going to work very poorly. And doing this thing of adding the intercept, people in machine learning call this intercept, is not really going to help us, right? Because if we move it, it's not really going to work very well. So in this example, we would like to have a classification rule that does something like this, right? And then inside the circle, one class, and outside the circle, another class, right? And how to achieve this with this sort of thing is very easy in this example, right? So we can define the feature representation to be just x1 in R3, x1, x2. We are going to make it go to x1 square, x2 square, 1. Right. Okay. So if we do this now, so this is the picture in the original features, right? In x1 and x2. if now we make the picture, so we are going to call the components of the feature mapping. So this is going to be the first component, this is going to be the second component, and this is going to be the third component of the feature mapping. If we make this picture, now instead of the original x1, x2 in the feature space, x1 and x2, right? So how is the picture going to look like? Anybody? I would like to ask. I think it's more interesting if we make it interactive. So anybody. So what happens? So these are my samples, and now I do this little transformation. Where are the examples now? After I do this transformation in this space, in the space of C1 and C2.
You are taking polar coordinates. Then you will have them like being like linear, let's say, like above pluses, below ones, minus.
Yeah, right. So exact. So basically, the points here, right? I mean, if this is, I don't know, if this is C, right? The points inside this circle is x1 x squared plus x2 squared smaller than c squared, right? Right. And then see, if I do this transformation, basically the points inside the circle are the points in which c1 plus c2 is smaller than c squared. So in terms of c1 and c2, the positive points are points that are all of them in this triangle. Right. They cannot be negative because we are doing the squares and so on. And right, so this is C1 plus C2 is smaller than C2, so this is right. So all the pluses are going to be in this triangle, and then all the minuses are going to be yeah, right. And now this is something that we can classify very easily with a linear rule, not going through the origin. That's why I put the 1 there, right? So now, if we work in this space, getting a classification rule like this circle is going to be linear in this space, right? Okay. Okay, so this is a very simple example, and then you might be thinking, yeah, sure, but this is because this example is just made to be that simple, right? And it's true, right? I mean, if I make this not to be in the origin, or maybe not to be exactly like 2 circles and so on, it's not going to be as simple as that, right? And that's true. So, okay, so just a comment before we do the general thing, right? So in this example, I knew that this is the right feature mapping to do because I made this figure and I thought a little bit and I said, oh yeah, this is this equation, right? When the features come this way, just because somebody thinks about something or knows about the data set, and they call it like feature engineering or something like this, like you use expert knowledge, right? So maybe somebody working or knowing how this data set is obtained might know, yeah, here what matters is the product between the first feature and the 10th feature, and then the square of the third feature is also important, right? So somebody might know which kind of features are important or what kind of relation among the features is important, right? So there's some expert that has been studying the data set tells you should do this, right? Something that is done in practice all the time, but of course it's not something easy to analyze mathematically, right? Because it's just some creativity of somebody, right? The good news is that, well, I mean, I knew how this was, so I used this feature mapping, right? So if I didn't know how these things are, and I do a feature mapping, if I do a feature mapping like, let's see. So I do a feature mapping, 1 of x2, and then the feature mapping is going to be, I'm going to keep x1 and x2 because I don't know if that's going to be useful or not. And then I will start doing this, and then maybe I will do x1 times x2 because who knows, maybe it's useful, and then x1 cube, and then x1 2 x2, and blah, 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 blah. And then maybe I put also constant just in case the constants are useful, right? So I can put a list of functions that might be useful. I don't know exactly what is going to work well or not, but if I put so the idea is that if I put a long enough list of functions, some of them are going to work well. And so if in this example, instead of just doing this, I do something like this, if I do something like this, it will also work, right? Because basically when I find the muse, if my optimization, if I have enough number of samples and so on in my optimization, I'm going to realize that the components of the muse for these guys are going to be 0, etc. Right? Okay, so that's the plan. Of course, this has also dangers, right? As you might also imagine, if I keep putting more things, I might end up having the overfitting problems we said before, right? So if I use polynomials like this, right, and I keep putting more and more polynomials and more degrees and so on, and then I might have a function, right? So if the function is a combination of polynomials with very high degrees, this function is going to be oscillate a lot, right? So I might end up having these problems of overfitting, in which, well, okay, we are going to discuss more later. Okay, but I guess you pick the idea of what's the plan, right? So the plan is to consider a transformation into a feature space in which D is going to be very large. So we want to transform our original X into very large vector, because if we have many components, the hope is that some of them will work nicely, and even just doing a linear rule. Yes, sure, good.
In the rest of the examples, you consider the real case, which is a particular case, but the general definition may use another kind of spaces.
Right.
In the feature mapping, the arriving space has to be necessarily RD.
Not necessarily. Not necessarily, but it has to be a space that has inner product structure. So this space is going to be the feature space. It's also going to be a Hilbert space. It's not going to be necessarily a kernel Hilbert space, but yeah. So it has to be a nice structure, basically because in here, right? So in here, we need to do inner products of the features with some vectors, right? So we want that this space has a structure in which we can do inner products, at least define distances. Okay, so that's the plan. So we are going to transform the X's into a large dimensional space. D is going to be very large, even D is going to be infinite. And tomorrow I will explain what I mean with this. So the case in which this D is very large, I guess is intuitive for all of you what it does. So it's just keep putting more and more functions here. The fact that we can even go to infinite dimensions might look a little bit strange, but it's not going to be strange in one day or two. Okay, so and that's so basically the idea is that if we go to very high dimensional space, the set of functions that we are going to consider are going to be combinations of many functions. Let me remove a little bit. No, okay, I think it's fine like this. So basically, we are going to have many functions. So we are going to have many functions of x, and the linear combinations of all these functions are going to give us something very general set of functions, right? So for instance, in here with this type of components, I can have any polynomial of degree 3, right? Just doing linear combinations of these monomials, I can get all the polynomials of degree 3. If I keep adding more and more functions, I will have more and more complex. So these type of functions are going to be more and more complex, right? So the plan is that we are going to have very complex functions, but not too complex. Okay, so just enough, right? And those are going to be these reproducing kernel Hilbert spaces, sets of functions in which we can do classification rules just as if they were linear rules. We can avoid overfitting because these functions are going to be simple, smooth, but they are going to be very general. So for instance, we are going to show that with this type of ideas, we can have functions that approximate any continuous function. Okay. When I mean approximate is with all the accuracy that you like. Okay, so we are trying to have both things, something very complicated, but at the same time tractable. Okay, and to finish this part, I'm just going to make a couple of comments, yeah, and then we start defining things, right? So basically, the idea is that we are going to consider sets of functions like those ones over there. So we are going to consider functions from x to r that are going to be defined like this for some feature mapping. And the set of functions that we are going to consider are going to be this reproducing kernel Hilbert space. And basically the idea is that these are complicated enough to be able to approximate basically anything that we want to approximate, but simple enough, smooth enough, so that we can do the optimization in a tractable way, and we can also avoid overfitting. Okay, so that's the plan. And then some things that are going to be useful and that now might look a little bit strange are two main properties we are going to have for these spaces of functions. So the first one is that we are going to have a function k. So we are going to have a function k of two variables. So this function k is going to be a function of two variables. It's going to be the kernel. So we are going to have a function k of two variables such that inner products in feature space, inner products in feature space, let's do it like this, the first time, inner products in feature space are going to be given by the values of the kernel. So that's useful because if I have a function like this, if I know this function, right, and I have a way to evaluate this function for every pair x and x prime. If I have this function and I know how to evaluate it, if my algorithm only uses the scalar products, inner products of the in feature space, like distances or angles or whatnot in feature space, I don't even need to know what is the feature transformation. Right? So this is important thing. And so if I know that there is a kernel function satisfying this and I know how to evaluate this, every time I want to evaluate an inner product, I just go and evaluate this, I don't even need to know what C is. I don't need to actually do the output of C. I don't need to do all this possibly complicated operation if this is high dimensional. Okay, so that is what people call the kernel trick. This is the usual way people call it. So basically the plan is that, yeah, sure, we are going to work in a very high dimensional space, but we will never explicitly do operations in that very high dimensional space. We will be just using the kernel, right? So that's what people call the kernel trick. And so this is the first important property. We will see in a minute why this happens. And then the other type of property that now might seem very strange is that, well, these functions are going to live in a Hilbert space, and then if I do the inner product of functions in that Hilbert space with sections of the kernel, okay. So with this notation, I mean, so the kernel is a function of two variables, right? If I fix one of the two variables, I end up having a function from x to r, right? So this is what I mean. So this is the function from x to r in which I have fixed the first input. Okay, so this is a function from x to r. It so happens that is going to be also in the Hilbert space. This we will show in a minute. And then if I do this inner product, the inner product I'm representing like this because I mean the inner product in this Hilbert space. If I do this, I end up having a number, and that number is indeed the value of x evaluated, the value of f evaluated in x. So this, the first time you see it, is like, what? How is this? And this might look strange after the coffee or whatever. We are going to see that this is not anything strange. This is just very simple and linear algebra consequence. But okay, but this is also very useful. This is what people call the reproducing property. Okay. So basically, this is also very useful. This basically means that if I know how to do inner products in the Hilbert space, inner products with my kernel, anytime I want to recover the value of some function in there in some specific point, it's just a matter of doing the inner products. Okay. So basically, the plan is that we are going to work with functions in this space, but basically just using the kernel, either inner products or. As I said, now this might look like this is I don't know if magic, but it's strange. But in a minute we will see this is not. This is very simple. At least it's very simple always, but in some cases it's. Okay, so this is the part of the motivation. Questions, comments, something that is not clear. Notations are clear. I hope I will try to keep the same type of nomenclature. Okay, so before we go for a coffee at 11, I'm going to do something in 5 minutes, and then we define these Hilbert spaces in a simple case in which everything is linear algebra, very simple linear algebra. All of you are familiar with these things. So I'm saying that everything is basically linear algebra. So first, I'm going to make a comment, right? So we are talking about functions from x to r. We are talking about functions from x to r. A very straightforward comment. I guess all of you have seen this and maybe use it, but it's a good thing to remember. So if I have a function from x2, if I have functions from x to r, it doesn't really matter what x is. These objects form a linear space. And this, indeed, this set is usually represented like this, like with the exponential object. So this set is a linear space just because we can define the sum between two functions just adding pointwise. Okay. So if I have two functions, we can define the sum of two functions just by adding the values of the two functions. And we can also define the product by the scalars just by doing the this is. I was going to say trivial. It's not trivial. It's straightforward, right? And I guess you have seen all of this, right? So it doesn't. So for this, it doesn't matter what is x. So this is always a linear space. This is always a linear space. Depending how simple is x, this linear space can be very complicated. So after the coffee, and this linear space is going to be very simple because x is going to be finite. Okay, so if x is finite, if x has t elements, if x is a finite set, then the set of functions from x to r is the same as the Euclidean space of dimension t in a straightforward manner, but that is good to recall. So if I have a function, from x to r, and x can only take a finite number of values, t different values, maybe t is huge, but a finite number of values, a function from x to r, we can see it either as a function or as a vector in RT. And the vector is just going to be the values of the function in the t different elements of the space. Okay, so this is straightforward, but it's important to keep in mind. Functions are going to be vectors, and vectors are going to be functions. So everything is going to be just linear algebra, just matrix multiplications and this sort of thing. Okay, so after the coffee, we will be defining the reproducing kernel Hilbert spaces, kernels, features, all of that in this specific case in which everything is just linear algebra. Okay, and the general case is going to be basically the same thing plus some technicalities. Let's say. Okay. So today after the coffee, we will avoid all the technicalities working in this case. I think it's good to start in this case so that you see everything is very simple. If at some point later you don't remember some property of this, you can think of it in this case and just do the operations with your in a piece of paper with matrices and so on, and then say, okay, yeah, sure. And then in the general case, it will be the same. Yeah. So the general case we will discuss tomorrow. Today after the coffee, we will discuss. Okay, so now let's go for a coffee and come back in 10 minutes. Okay, very good. So let's get back to reproducing kernel Hilbert spaces. As I said before, we are going to do now the simple case of finite dimensional reproducing kernel Hilbert spaces. Basically, the idea is that everything is going to be linear algebra, and indeed, in this case, all the subspaces are going to be reproducing kernel Hilbert spaces. So basically, in the general case, the set of functions that are reproducing kernel Hilbert spaces are functions that are nice enough to behave as vectors in finite dimension. That's one way to put it. But we will talk about the general case tomorrow. Okay, so as I said before, in this case, x is just going to be the different values, so that the set of functions is going to be the same as the Euclidean space. In the next 40 minutes or so, we are going to be working on this space. Everything is going to be vectors and so on. As I said before, it's very easy to translate a vector into a function and a function into a vector, but for now, we are going to just work on over vectors, and then maybe later we can see how the things that we develop translate into functions. So as I said, this equivalence is straightforward, but it's important to keep in mind. Okay, so we are in the just some Euclidean space, possibly of very high dimensional, but just in a Euclidean space RT. And we are going to start defining all the ingredients, the Hilbert space, the inner product, the kernel, features, etc. Okay, so we live in just an Euclidean space, and first we are going to start from features. So first of all, we are going to define the reproducing kernel Hilbert spaces starting from features. Okay, so we are going to have the features just as before in the motivation, right? So we have the features. The features are just each component in the feature representation, and each component in the feature representation is a function also from X to R, right? So each one of the features, each one of the components is also a vector, right? So functions are going to be vectors for now. So these are just the specific vectors in RT, right? So as I said, for now, everything are going to be vectors. If you might want to keep translating what does it mean, the functions to vectors, so we can do everything at the end. Everything is very simple. It's going to be basically a matter of being careful with the notation. Anyway, so features are going to be the specific vectors in RT. So the features are going to be some vectors in RT. Let's think that we are going to have some features, vectors in RT. For what I'm going to do next, I'm going to assume that they are linearly independent. This is not necessarily, this is just to make our life slightly easier. If there is time today, I'm going to do the general case in which they are not linearly independent. In practice, you don't really want to need that the features are linearly independent, right? Because as I said before, the plan is that we are just going to put multiple components. You don't really want to be checking, oh, is x to the cube linearly independent of the square root of x 3 times whatever, right? So everything works if they are not linearly independent, but it's slightly easier the formulation with linearly independent. Okay, so these are the d vectors in RT. They are going to be linearly independent, and then we can directly define what's going to be the set of functions or the set of vectors in this case, right? So the set of vectors, I'm going to call vectors f because later are going to be functions. So the set of vectors that we are going to consider are going to be just linear combinations of the feature mappings of the features. Right? So we have the specific vectors in RT, and we can form the linear combinations of them, right? Just the coefficients are just going to be any real number. So basically, this is going to give us a subspace of vectors or functions H, just the linear combinations of the features, right? And that's basically. I'm trying to keep the same notation as before, so you see that this is just the same thing as before, but now we are thinking in terms of vectors instead of functions. So that's going to be the space of functions that we are going to consider, just linear combinations of some D specific features. It's going to be useful to use a matrix notation to describe it. So this is a vector. This is a linear combination of these specific vectors. So we can write this as some matrix times vector mu. The vector mu is just going to be the vector formed by the coefficients. And the matrix C is just going to be a matrix in which we put these vectors C1 to CD as columns. So this is a matrix in which every column is one feature, right? So this is a vector in Rd, and this is a matrix with T rows, right? The size of each vector is T. We live in Rt, and the number of columns is C. Right? So everything just very simple linear algebra, nothing complicated. So the space of functions are just linear combinations of these features that we can represent as just the natural way or in a matrix form that way, right? So everything very simple. Okay, so this is the space of that we are going to consider. And since this is going to be a Hilbert space, we need to define, in addition to the space, we need to define the inner product in it, right? So if we have two vectors in this subspace, we are going to define the inner product in this subspace. Okay. So anybody has some idea how to define the inner product? So everything is going to be quite natural, but how to define the inner product here? So the the subspace is going. So the Hilbert space is going to be given by the features. So the space is given by the features in the sense that it is given by combinations of the features. The inner product is also going to be given by what specific features we choose to use. Right? So the inner product, I mean, to define the space, we could have chosen different vectors inside this subspace, and this will give us the same H. For the inner product, is going to be important what specific features we choose. So what's natural way to define an inner product based on the features and based on what is subspace is? Anybody has some idea how can we define an inner product? Well, so what is an inner product? I guess it's clear for everybody, right? So it's something like a scalar product, but not directly. So the scalar product between f and g will be just doing the scalar, just the multiplication transpose times g. So we want something that is bilinear and so on, but is something defined only for the elements of H. So what's the simple, natural way to define this inner product? Anybody has some suggestions, some ideas? Don't think anything complicated. So the elements of H are just combinations of the features, right? And they are just so any vector in H is going to correspond to a vector mu, right? So for instance, so F is going to correspond to some mu for F, and G is going to correspond to some mu of G. Was natural way to define the inner product between F and G. Well, we could do just the scalar product of the mu corresponding to F and the mu corresponding to D. That's maybe the most simple way that everybody can, right? So if the vectors in H are just corresponds to different combinations of the features, and these are given by mu. We can define the inner product just by the standard inner product of these guys in RT. Okay, so few things. Well, so this inner product depends on what specific features I use, right? So if I now generate this subspace with the different features, the inner product is going to be a different thing. More comments that maybe you are thinking, is this okay, right? Can we do this definition and that's it? Well, so first of all, is this well defined? Is this well defined? Well, this is well defined because I'm doing this case. So if the features are linearly independent, for every vector, there is only one choice of mu. So if these were not linearly independent, for the same vector, I can have two different mu's. And if I have more than one mu corresponding to the same f, this definition wouldn't make sense. I mean, we can do it also in this case, and if there is time, I will do it later, but this is well defined because these are linearly independent. So each f has one and only one mu, because this is linearly independent, right? So this is well defined thing. And the fact that this satisfied and this is bilinear and symmetric and so on is just straightforward consequences of the scalar product here. Right? So you can very easily prove that if I do f1 plus f2 inner product with G, is going to be linear in both components and also symmetric just because of the properties of the scalar product. Okay, so we just found out what's the right notion of inner product, just basically because of the definition of the space, right? What else? Okay, so with this inner product, yeah.
Why not put VF transpose K VG?
K, what is K?
C transpose C.
Okay, yeah, we will get there. We will get there. Okay, good. So you are ahead of the course. We will get there. Yeah, this is yeah, we will get there.
So you assume for that the vectors are not only linear independent, but they are also orthonormal?
So they are going to be. So they are okay. So this is also a comment that I'm going to make now. So in orthonormal, you mean in the standard inner product of RT? No. So they are just, in terms of RT, they are just the linearly independent vectors. So the comment I'm going to make is that if now, so of course, each one of the features is a vector in H, right? It's just the vector in which one mu is 1 and the other mu's are 0, right? So if now I do the inner product of two features in H, so the features live in H, I can do the inner product of them. And now if I do the inner product of them, well, basically, Ci is, so the mu's corresponding to Ci is just the vector of zeros and then a 1, right? And now when I do the inner product following our definition, this will be, just that scalar product, and that will be 1 if is the same feature and 0 if they are different, right? So the features are orthonormal for the inner product in the Hilbert space. As vectors, so in here I can choose any vectors, right? So before when we were talking about the motivation, I was just throwing out the x squared and whatever. I was not carefully choosing, okay, this has to be orthonormal with the other thing and so on and so forth. Any vector in RT will do. These vectors are orthonormal for this inner product. Okay, so this is good, and we will get in a minute with the things that you were saying before. What else should I say about this? No, I think that's fine. Well, little additional comment. Of course, this construction is not unique, right? So I can start with a different set of features and end up having the same Hilbert space. So if, because every space has many different orthonormal set of vectors, right? So if I choose other set of vectors that are also orthonormal for this inner product, the Hilbert space is going to be exactly the same. So the features are not unique. There are multiple features that are going to give me the same Hilbert space. Okay, so those are the features, and now let's see what is the kernel and how do things using the kernel instead of the features. So in the motivation, right? In the motivation, basically we were thinking that the idea is to represent each element of X with some vector in this Hilbert space, right? So now in this case, we have a fixed number of elements in the space. So we are going to represent each one of these elements with a vector in H, following the same ideas as what we did in the motivation, right? So H is the set of functions that are C times mu, right? For some coefficients mu. So if we want to represent X in here, what we can do to represent X is just to use as mu the features evaluated in that Xi. And so this is right. So this was our plan, to represent X's as vectors, just to pick the features and represent the value, right? So we can represent each point in the Hilbert space by using the coefficients given by that specific points and the features. So this vector here, in terms of this matrix, so this vector here, so the matrix is the matrix formed by C1 and CD in columns, right? So this vector here is the ith row of this matrix. Yes. So the functions, the way we translate from functions to vectors is just right. So this number is the ith component of the vector C1. Right? So this is, as I said, straightforward, but it's good to get used to it. So this number is the ith component of this vector. So these components here are the ith row of this matrix. Yeah. So the plan is that we are going to represent each element in X with the vector in which the mu is the ith row of this matrix, and when we put that in column, the ith row is going to be the ith column of the transpose of C. And this might take a few seconds to see. I mean, but this, at the end, as I said, this is just a linear algebra, right? So if you get confused, you can just pick a pencil and a piece of paper and see, right? So this is the ith row of this matrix, which is just this, and then, so basically we are going to represent each element of X with this vector, right? So this is going to be a vector in H. This is going to be a vector in H, just because the vectors in H are represented like this, matrix C times some vector. C times some vector. So this is going to be a vector in H. And this vector, we are going to denote as K sub I. And we are going to call it a section. Okay, so these K I vectors are vectors in H. We can define it for every element in X. We can define this vector in H, right? So we are going to have T vectors, K1, Kt. All of them are going to be in H, and they are defined this way. Okay, and these are going, and this we are going to call sections. The idea why we decided to choose these vectors in H is because basically they represent each one of the elements of X in the way that we like, as vectors and given by the images of the features in that specific case. So, as I said before, everything is in an algebra, but it's like a little bit confusing the first time you see it. Everything I'm doing is just very simple linear algebra, matrix multiplications, and so on. Right? So, okay, so these are vectors in H that are defined this way. So these are going to be sections, and then the matrix C times C transpose, which is what we were pointing out before. I'm going to give it a name, and I'm going to call it a kernel. So this is going to, so this is a matrix. So this is a matrix. This matrix has T rows, right? And also T columns. I'm multiplying these two vectors, these two matrices. This matrix has T rows and T columns, and okay. So this is a T times T matrix. This matrix, so this matrix, since it's defined this way, is going to be a semi-definite positive matrix, right? Because it's a product of two matrices. Well, first of all, it's symmetric, right? Because it's like this. So this matrix is, we are going to call it the kernel matrix. And this is always going to be symmetric. And it's going to be semi-definite positive. Just because it's a product of a matrix times its transpose. So this is going to be the kernel. So this way we have found what the kernel is just using the feature. So we started from features and we found out what is the kernel. Now let's see what kind of things we can say from this. Well, first of all, the sections. So the sections are the columns of the kernel matrix. Right? This is just okay. So these vectors in H are the columns or the matrix K. Just that's the way we define it. And since the matrix K is symmetric, they are both the columns and also the rows. Right? So the sections are going to be just the columns or the rows. So if you like, we could also write these vectors as pick the matrix K, fix one row or one column, and then vary, fix a row and then vary the columns, or the other way around, right? Just wait, right, and this maybe you can connect with the things we were talking before. We will translate everything in terms of functions soon, but okay, so the sections are just the rows or the columns of K. K is defined from the features this way. What else? What else we can say about this? Yeah, maybe we can start defining things just from the kernel. What else? Okay, just a simple. Okay, let's start making some observations after we have this new objects. So all the sections are elements in H. So what happens if I do the inner product between two of them? So if I do the inner product between these two vectors, I mean, I'm allowed to do it because all these vectors are in H. So if I do this, so let's recall what's the definition of this. So each section is she transpose EI, right? And then we said the idea to make the inner product is we can represent the vector as C times some vector mu, and then just do the scalar product of the vectors, right? So the inner product of this will be the scalar product of this vector times the one corresponding with Kj, which is going to be like this, transpose, right? So just doing very simple linear algebra, when we take the transpose of the product, we get this times this times this. Very simple. So this is the kernel matrix, and then if we do this operation with the kernel matrix, we get the kernel matrix evaluated at the row I, column J. Right? So this is matrix K. Right? So the inner product between two sections is going to be the kernel matrix in the coordinate corresponding to that row and that column. Everything just, I mean, I'm using elementary linear algebra, right? So, okay. So this is a simple property. Let's do a little bit more of these simple properties. What happens if I pick a general vector in H and I do the inner product of some of the sections? Right? So I pick general element in H. General element in H is given like this, and I'm going to do just the inner product with one section. So just following the definition of the inner product, we will do the scalar product of mu with the vector and representing this, which is just G transpose AI. Right? I'm just following the definitions and very simple linear algebra, right? Well, this guy is C mu transpose EI. C mu is F, right? So this is the inner product between the vector F and the canonical vector EI, and that's the ith component of vector F. We see it as a function will be the value of the function F evaluated in Xi, right? So by just elementary linear algebra, we arrive to the reproducing property that looked very strange before, but it's just okay. Elementary linear algebra. Okay, so yeah, everything that I did in the last 10 minutes is elementary, but well, if you get distracted, you can just do by yourself. It's just everything follows from the definitions. Okay, good. So this is the sections. This is the kernel, and we started from the futures to do everything, right? But now that we have the kernel, we can do everything just using the kernel. This is also one of the important ideas that if we know the kernel, that's enough to work in this with this type of function. So let's do that. Let me see if I am forgetting something I wanted to say. No, I think this is fine. Okay. So now, we are going to define the Hilbert space and the inner product of using the kernel. Right? So how to do this? Well, first of all, each of the sections are vectors in H, right? So if I do linear combinations of the sections, so if I consider functions that are linear combinations of the functions, these functions are going to be in H, just because each one of the cases are in H, right? So this set of vectors is in H. And so you think it's smaller than H, the same as H, the same, smaller, it's the same. Okay, so the fact that this containing H is just because the cases are in H, and the other way around is just because of the dimensionality. So these F's are just, I pick the matrix K, and I multiply by a vector of alphas, right? So we can write these vectors in this extended form or just in this matrix form. K is the kernel matrix, the columns are the K's, and alpha is just a vector given by all the alpha. Right? So these vectors, I can write them like this, it's just more compact. Now, this linear subspace is contained in this other linear subspace. The dimensionality of this linear subspace is the same as the rank of K, right? Since K is the matrix C times C transpose, the rank of K is the same as the rank of C, which is the dimension of the feature mappings, and in this simple example is the number of features. Okay, so the dimensionality of this is the same as the dimensionality of H, right? And since one is containing the other, they have to be equal. Okay, so this, I'm doing all the steps, but maybe later I'm gonna skip something. I'm just doing all the steps slowly so that you see that all the arguments are elementary. Okay, so we could define the Hilbert space just using the kernel without even knowing what are the features or thinking about the features, just using the kernel. So this will be the Hilbert space. And now we can also define the inner product just using the kernel. So if I have two functions, let's do it like this. So one function is with alpha and the other function is with beta, let's say. What's the inner product of these two functions? Well, K is C times C transpose alpha. C times C alpha transpose beta, right? I'm using the previous definition of the inner product. The inner product is the scalar product of this vector times this vector. So it's C transpose alpha. C transpose beta, and that's alpha times C transpose beta, which is alpha K, right? And that's basically what you were doing before, right? So why not use the kernel? I mean, it's the same thing, right? So basically, exactly the same inner product we defined before with the Psis. We could as well just define it using the kernel, even if we don't know what the features are. We can define both the set of vectors or functions and the inner product. without using the features or without even knowing the feature. So, what else? What else I want to say about this? No, I think this might be enough. Okay, so we could, in the previous discussion, we started from features and then we found out what is the Hilbert space and what is the kernel and what is the sections and everything. We could as well just define the reproducing kernel Hilbert space starting from the kernel. Right, so if somebody comes and give us a kernel, basically if somebody comes and give us a matrix, E times T, that is symmetric and semi-definite positive, right? That would be enough, just by having the matrix. If somebody comes and give us the matrix, we don't know what the features are, but it doesn't matter, right? So if we just know the kernel, we could define the space of vectors just using the kernel. We could define the inner product. We could define the inner product just using the kernel. And what else? Yeah, that's it, right? So we could, I mean, and of course, we could define the section just as picking the columns or the rows of the kernel, right? Okay. So let's do a small proof. So before I was saying that I mean, we can start from features and define everything, right? And I said that construction is not one-to-one because we can have two different set of features that give us the same Hilbert space H, right? With the kernel, the construction is unique, right? So let's do it little resolve. Very simple. So basically, the kernel is unique, right? So for each reducing kernel Hilbert space, we will only have one kernel. We might have different set of features, but only one kernel. So let's prove this. What should I do? So prove. Very simple. So I guess how you go about these proofs, it should be kind of direct. So let's assume that there are two kernels and see what breaks down, right? So let's imagine that there are two kernels. So if there are two kernels, let's say K and K tilde. So if we have two kernels for the same reproducing kernel Hilbert space, if we do the inner product of the sections of the first kernel with the sections of the second kernel, what would happen? Well, so since K is a kernel for that Hilbert space, when we do this, on one hand, we will get the section Kj, the if component of the section Kj, right? Before we saw that when we do the inner product with a section, we end up obtaining the component of the other vector corresponding to that section, right? So that was the reproducing property, right? If well, so here if K are here for the same H, right? So if we do this inner product, on one hand we get this because the K is a kernel. If K tilde is also a kernel, this will be also equal to Ki jet, right? Because we can use the reproducing property right? So because both K and K tilde are kernels, we can use the reproducing property for both things. So then this is equal to this and also equal to that. And since kernels have to be symmetric, that means that these two matrices are the same. Yes. So kernel matrix is only one. Each reproducing kernel Hilbert space can only have one kernel matrix. And the last thing for this, right, so here we started, before we started from features and defined the kernels and the sections and everything. Now we started from the kernel and we define the sections. So I think the missing part is defining the features from the kernel, right? So that's also very simple, right? So the matrix K is a symmetric definite, semi-definite positive matrix. So we can factorize K as some matrix times its transpose. Right? So for any symmetric semi-definite positive matrix, we can factorize it this way. Not in only one manner. There are multiple ways to factorize a matrix like this, right? Each one of that factorization will give me a different set of features. Right? So we can find the features from the kernel just by factorizing the kernel matrix. And one way to do this would be like finding the eigenvectors and eigenvalues of the matrix K, and then just using the trivial eigenvalue composition, finding the features from the eigenvectors and the eigenvalues. Okay, good. And in here you can also see why the features are not unique, because this can be done in many ways. Right. Okay, so yeah, I think we covered a lot of things. So okay, yeah, so let's do maybe 2 comments, at least one. Okay, so now we have been working just with vectors. Let's translate things to functions, right? And let's see, for instance, the 2 properties that we were talking before, right? So the features. So features are vectors in RT, which mean they are functions, and then each feature is going to be a function from X to R. We already talked about that. Kernels are going to be matrices from time T to T, which means that we can also see the kernel as a function from X to X to R, in which if I have a specific pairs of X, okay, let's do it, right? So X is a finite set, so each specific X is going to correspond to some Xi and Xj, and the way we do this correspondence is by taking the, right? So the way we move from vectors to functions is just by the value of the function is the component of the vector. What else? I think that's basically it. So yeah, now we can see the 2 properties we were saying before, right? So before we were saying that X prime is going to be the inner product of Cx times. Right? So that was the kernel trick, right? But that's just that's what we call the kernel trick before. But in here is just the way we define it. Things. Okay, let's do it. We have 2 specific x's, and then this is the ith. So this is the vector formed by the ith components of the features, which is the ith row of matrix psi. which is t, right? So this is in terms of functions. If we see it as vector, it would be this, right? And then this other guy is the vector. I'm doing it right. Yes, I'm doing it right. Right. So it's going to be a column vector. Right. So this is going to be. So this is the jth row written as a column, which is this you can do it slowly, more slowly or whatever, but it's just direct consequences of the definitions, which is just K, I, J, right? This is the matrix K, which is just this. Okay. So, so the kernel trick, let's say, is just a matter of translating vectors into functions and so on, right? And in terms of vectors and matrices, it's just a straightforward consequences of the definitions. And also the reproducing property, we already saw it, but let's do it again. So let's see this. Right, so if we see the kernel as functions, when we do the inner product with one specific section of the kernel, that's the same as doing f in the section vector that we said before. And before we said that this is the if component of the vector f, which is the f evaluated in xi. So, yeah, I didn't do anything, just translating vectors into functions and so on. Okay, so everything is just a very simple linear algebra. You just need to mention carefully. Okay, so today we did it for the case of finite x, so that everything is linear algebra. You can do it in piece of paper, everything very easily. Tomorrow we will do the general case. We will see that it's basically the same thing. In the finite case, every subspace is a reducing kernel Hilbert space. In the general case, when x is not finite, we will need some regularity conditions. And so not all the, of course, not all the set of functions are reproducing kernel Hilbert spaces, but the interesting cases are. And now, I don't know if you have questions, we can talk about it. If not, maybe in a couple of minutes we can do the case with not linearly independent features or something like this. That's the only thing missing. But I don't know, that might be boring. If anybody has question, comments, something that is not clear. Okay, so let's do the case with non-linearly independent features. Not really relevant. Well, first of all, we have two choices, right? So either start with features or start with kernels. If we started with features, I did it for the specific case in which the features are linearly independent. If we start from kernels, there is no limitation, right? So when I said the kernel, we can decompose as some matrix C times C transpose. The rank of this matrix C does not need to be full rank. So that also shows why it's not necessary to have linearly independent linearly independent features. But from the first construction, if they are not linearly independent, we are in a problem, right? Because if the features, so now features are not linearly independent, right? So if the features are not linearly independent, the same vector, I can write it with different means, right? So if I define the inner product just using the mu's, I am in trouble. I am in trouble because which mu should I use, right? If there are multiple mu's, if I use a different mu. This scalar code is going to be a different thing. So how to define this inner product just from features? Okay, so basically the way to do it is so I can have multiple mu's. And so I'm going to define the norm. Let's do it just for the norms. So I can define the norm. There are multiple mu's I can choose. I can define the norm by considering all the mu's such that f is mu. I can consider all the possible mu's and then pick the smallest scalar product among all these mu's. I guess this is something reasonable to do, but let's see why this works. Okay, let's see why this works in a couple of minutes. Okay, why this works? Well, first of all, just doing the norm is enough. I want to define the inner product, but if I know how to define norms, I also know how to define inner products. That's also a simple thing to do. Why this works? Well, so in order for this to work, well, we need a definition of the inner product that works always. That is the one with the kernel, right? So we know that if f, so if this f is c times c transpose times alpha, right? So every f we can write it this way or this other way, right? So we know if we write it this way, meaning using the kernel, we know how to define the norm. The norm is going to be alpha transpose the kernel alpha, which is going to be alpha transpose c transpose alpha. Okay, so we know how to define it right if we use the kernel instead of the features, but we also would like to know that it's possible to do everything just with features, right? So basically, what we need is to solve that alpha times c transpose alpha is the same as making the smallest value of these two things for the mu's such that c times mu equal to c transpose alpha. Let me see if okay, so this is what we have to prove, right? So we want to define using just features, we want to define the norm this way. In order for this definition to be the right one, we need to get the same result if we do it from kernels or if we do it as we are trying to do. Right? So we need to prove that both things are equal. Okay, so let's do the proof. Proof is maybe not as straightforward as the previous one, but the kind of ideas might be useful for later, so let's do it. Okay, so so basically in here, I guess you can see what we are trying to achieve, right? So we are trying to solve that the mu that minimizes this quantity is this specific mu here. If the mu that minimizes this quantity is this specific mu, we have what we want. So we are trying to show that if we are considering mu's that satisfies this, the smallest norm is going to be given by the norm of this specific. Okay, so let's do this. Okay, so so the set of mu's that satisfies and this thing, the set of mu's that satisfies that thing is, well, this is one of them. This is one of the mu's that satisfy this thing, right? Because if I pick this, I multiply by, okay? So this is one of the mu's that satisfy this. So this vector is a vector in this set. This set is easy to see that this set is an affine set. So we are going to prove that this set is the set of vectors that can be written as C transpose alpha plus some linear subspace that is going to be the kernel of C. Let me see if I right. It's fine. Okay, so we are going to see that this set of vectors is the same as this other set of vectors. This set of vectors in the right is the set of vectors formed by this specific vector plus some vector in this linear subspace. When was the last time you had a course in linear algebra? But this is okay. Okay, so we are going to prove this, and after we do that, we basically will be done. So, well, first of all, the inclusion like this, the inclusion from the right to the left is direct, right? If I have a vector that can be written like this, and I want to know if it's in here, what I do is I multiply it by Xi, and I check if it gives me this, right? If I have a vector here, I multiply by Xi, this will give me this, and if I have a vector that is in the kernel and I multiply by Xi, it gives me 0. So this is no problem, right? So to see the other inclusion, basically, we want to check that if we have a vector. So what we can do is, if I have a vector that is in this set, if I have a vector that is in this set, and I subtract this other vector here, I get a vector in the kernel of C, right? This is what I need to do to show the inclusion the other way, right? So, well, to check if this is in the kernel, what I do? Well, I just multiply, right? So if I do this minus C alpha, so the transpose alpha, do I get 0? Yes, right? Because mu is here. So this minus this is. Okay, so the set of mu's and that we are trying to do the optimization can be equivalently written this way. All right, so we are almost there. Okay, so basically our optimization is over vectors that are written the sum of this vector plus a vector that lives here. So we are doing the optimization over norms of vectors like this, x. Let me see if I don't want to mistake anything. And x is in the kernel of C. Right? Okay, so now what happens is that this specific vector is orthogonal to any vector in the kernel, right? So if I do, what's the easiest way to do it? Vector in the kernel. So if I pick a vector in the kernel, I get 0. Y is the scalar product of this and going to be 0 if I pick, yeah, right. So basically, x is in the kernel means that C times x is 0, right? So then, when I try to do the scalar product with this, I will be doing this times C times x, right? So when I do the scalar product of this times x, is going to be this, right? And since x is in the kernel, this is, okay, so this is 0. So the scalar product of this vector with this vector is going to be 0. And now if I do the norm of the sum of these two vectors, is I'm going to get okay, let's do it little by little, this transpose, right? I do the first with the first, and then if I do the scalar product of this with this, I get 0. If I do the scalar product of this with this, I get 0, and then I will have plus x. Right. So I'm trying to minimize that quantity, right? I'm trying to minimize that quantity, barring the x's in this subspace. So the best, the smallest value I'm going to get. Well, I'm doing the smallest value changing x. So the smallest case is going to be when x is 0. Okay. Every now and then it's good to do a proof carefully, but okay. So basically, we could have defined the inner product just starting from the features, defining it this way, but okay. So yeah, maybe with this we can finish. Yeah, question. Yeah.
Can you re-explain again why, like the first contention of the?
Yeah.
Yeah, that one.
This contention. Okay. So was this contention? Okay. So I have a vector in here, right? Slowly, right? So I have a vector in this set, and I want to check if it's in this other set or not. Right? So a vector in this set is a vector G alpha plus x when x is in the kernel, right? So this is one specific vector. So any vector in the right side is of this form, right? And now I want to check if this vector satisfies this quantity, right? So then to check that, I will do C times that vector and check if this gives me this. Okay. So the first part gives me what I want, and then the second part, since x is in the kernel, is going to give me 0. Any other question, comment? I mean, this little proof is not really relevant, but some of the ideas that we use to prove it are going to be used later in something called the representer theorem. So that's why I wanted to do it with some detail. Any other question or comment? Okay, so then we can finish here and continue tomorrow.